Well, I'd like to welcome everybody who succeeded in finding this room here and in transitioning from wherever they were through this large convention center to the Gilbert White Distinguished Lecture. And I know the effort involved, but I'm confident it will be worth it from what we'll hear today. The Gilbert White Award is the Natural Hazards Section's primary award and lecture, and there's been a long and complicated bureaucracy involved, but basically we feel it is both award. It's an award, and the awardee will give us a distinguished lecture. So I'd like to turn it over to our president, who will actually cite our honorees' accomplishments.
Thank you very much, Said. Welcome to everybody who have come to the room. And this is the talk given by Dr. John LaBrecque. And I believe everybody knows him, but this is my duty to read his citation. John LaBrecque has over 45 years of experience in research, engineering, program management for earth sciences with an emphasis on geophysical exploration techniques, including geopotential, seismic, and geodetic systems involving precision navigation of shipborne, airborne, and space-based platforms. Dr. LaBrecque led NASA Solid Earth Science program for nearly 25 years, including NASA's Geodetic infrastructure and research programs, and its satellite gravity, geomagnetics, topography research mission. John is a research fellow of the Center for Space Research at the University of Texas, Austin. He is the chair of the IUGG Commission on Geophysical Risk and Sustainability and led geohazards monitoring focus area of the Global Geodetic Observing Systems. Dr. LaBrecque is currently focused upon the application of geodetic science and technology for mitigation of natural hazards and disaster response. He has visionary for the natural hazards and disaster in future, and his current focus is the application of real-time global navigation satellite system technology to tsunami and earthquake early warning through the development of international collaboration. So let us welcome John, okay, and I would like to invite John to give the Gilbert White lecture. Thank you.
Thank you, Ramesh, and thank you to the committee that gave me this great honor, and I hope that I do you proudly here. When I have to admit, though, at the very start, when I was awarded this medal, I was not acquainted with the work of Gilbert F. White. And in fact, it was my introduction to Gilbert White began with this award, and then shortly thereafter, when I was walking through Boulder, Colorado, after a UNAVCO meeting, I came upon a flood gauge with a memorial to Gilbert White. He used to be the chair of the hazards group at University of Colorado at Boulder. And so he's well loved in that community. And what I've learned from Gilbert White and his work and the subsequent biographies is that he devoted himself to the advancement of the science of hydrology, and especially its applications to promoting peace and societal well-being. So he worked for safe water, he worked to try to ready populations or for resilience against flooding. He worked for the advancement of geography and science in general. And so I began to think about this and to try to mold this talk in a manner that would that I think Gilbert White would approve of. And my thoughts were that his love of hydrology really pretty much followed my own devotion to geodesy. And that the work that I've been trying to do, along with my many colleagues in the U.S. and many other nations, is to advance geodesy for the service of mankind, to promote peace, to improve resiliency, and to against natural hazards. So with that, let me begin this with a little bit. So the talk will focus first on space geodesy development plans. This sounds dry, but it's fundamental to the definition of the new geodesy, as this title implies. And then I want to try to speak briefly about some of the accomplishments that this these new geodesy plans have accomplished, and then applications of the global navigation satellite systems to environmental monitoring, and finally my own personal view for the advancement of GNSS for the augmentation of tsunami early warning systems. I think if there is a demarcation, one of the most important here is the publication of the something called the Williamstown Report. It occurred from a meeting of major scientists in 1969 rather, at Williams College. And if you'll remember that time, this was a time of great revolution in geophysics, because we were finally beginning to unravel the fabric of plate tectonics to understand it, and one ocean after the other was being deciphered. And so this meeting brought together the experts in geophysics and geodesy, and it was sponsored by the Department of Defense and NASA. And the Williamstown Report basically promoted or advanced the idea, among many others, many revolutionary ideas, that the nation should focus on the development of ocean altimetry satellites, and for which the first one, well, actually the one that really accomplished their goals was CSAT. And then gravity field satellites, that was accomplished through GRACE, and laser ranging and VLBI systems, which is currently embodied by the Global Geodetic Observing System, and navigation systems for basically short period or rapid positioning. And that's now done through GPS and then the subsequent constellations called the Global Navigation Satellite System. Now, if you want to look for a monument to this Williamstown report, it really was a seminal report and founded really modern geodesy. You only need to call up Google Earth, because the databases in Google Earth are fundamentally the land topography accomplished through the shuttle radar topography mission and subsequent topographic missions such as Terrace-RX done by the GFZ, the Germans. The oceanography, which is now done by David Sandwell at the University of California, but basically was promoted early on by Bill Haxby. And this is one of the products of geodesy because it's derived through the geodetic determination of the ocean surface, the primary component of which is the geoid, and topography is expressed within the geoid. So basically, geodesy drained the oceans to reveal topography. And what you see on this map also are these little green specks, which today are the distributed sites of GPS monuments. Now, more recently, in 2008, the Global Geodetic Observing System published GGOS 2020, which was their vision of how we should pick up after the Williamstown Report. And in the interim, there were many, there were many strategic, I'm just not doing this right. I've been told I'm not a very good driver, and so it's certainly true here. Here we go. All right, and this work really is based on technology and the expected performance of that technology in the decade to follow after the early 2000s. But as we all know, we have to fight against there are political forces at work as well as habits, which make these objectives difficult to achieve. And so we have to persevere as we move forward. The Global Geodetic Observing System is based primarily on 4 techniques and some very effective communication systems and computational capabilities. Those 4 techniques are very long baseline interferometry, recommended by the Williamstown Report, the ILRS, also recommended by the laser ranging system, recommended by the Williamstown Report, the Global Geodetic Observing, the Global Navigation Satellite Systems, GPS, and DORIS. And these all produce their own products, which are combined into a terrestrial reference frame. But they also provide tracking and the resolution of Earth rotation, all products that were envisioned by the Williamstown Report. And today's network is evolving, developing, because its new objective under GGOS 2020 is a reference frame which is accurate to 1 millimeter, and which is difficult to believe, but it's going to be achieved, or the concept is to be basically the co-location of all of these observing systems within very near to one another, so that their relative positions no longer influence the results. In the center of this, at the bottom, is the concept as it's being developed in Ny-Ålesund, one of the northernmost sites in Spitsbergen. And here the Norwegians have invested very heavily in developing dual VLBI receivers to diminish the effects of the atmosphere, and included will be high resolution laser ranging, as well as absolute gravimeters and several GPS receivers. Now, we're going to leave that behind and look at the GNSS systems, the IGS systems, which are a component of this reference frame and which depend very heavily upon the reference frame for accuracy. For example, when you look at GPS position, it relies on the International Terrestrial Reference Frame to calibrate itself. And so your positions are really directly received from or directly reliant upon this reference frame. It is basically, the GNSS systems are basically the way in which we access the International Terrestrial Reference Frame. Now, this fact, the availability of this navigating capability, which was proposed by the Williamstown Report, has been universally accepted. And in red here, you see the current state of GPS receivers stations globally. Now, we all know that there are many more of these because each one of our cell phones usually contains a GPS receiver. So you may be a transportable GNSS station or receiver, but these are fixed and very useful for providing relative navigation. The missions that were proposed by the Williamstown Report have had an enormous impact, as I pointed out, on the global Earth page, but has an enormous impact in mapping the Earth's surface. You can, from top to bottom here, the topography from TerraSAR-X now provides 10-meter topography globally, and it was navigated through GPS receivers, and the topography was gained through geodetic imaging of the ground surface. In oceanography, in fact, I was asked early on to put GPS receivers onto our oceanographic ships while it was still very much a prototype system. And the application here of swath mapping bathymetry was one of the ways in which we tested the accuracy of GPS. You need accurate real-time positioning to ensure this proper mapping. And then on the very bottom right, you have something called the UAV SAR, which is a synthetic aperture radar, only made possible through precision GPS, real-time GPS positioning. At the top right, oops. Let's see. Come on. Oh, great. It worked earlier. I don't understand why it's not working here. Well, oh, here it is. Okay, good. This is the GRACE mission. It's a mission that I was involved in since it was a gleam in the engineer's eyes. And I'm very proud of this mission. This is basically the mass balance of Greenland recorded during its mission lifetime from 2002 to 2016. GRACE was decommissioned this past October. And we were just astonished by the ability to measure gravity from space. Here you can actually see the seasonal variations in ice cover and snow and ice cover in Greenland. And when you combine that with lasers, you can actually measure the mass of newly fallen snow for each year because you have the volume change and then you have the mass change. So GRACE GRACE throughout the world has measured the changes in aquifer charge and flooding and glacial rebound, all of these issues that Gilbert White was very concerned about. In fact, I saw a particular map from GRACE that was focused on the Middle East and Asian subcontinent, and those areas that are particularly drawing on their groundwater at an unsustainable rate are also those areas that we find a great deal of social unrest. And so I think it's very important for us to continue focusing on new ways to identify and understand the distribution of water over the surface of the Earth. Coming in 2022, we all know that there are new GNSS satellites being launched. Russia with its GLONASS, Europe with its Galileo, and China with its Beidou, and of course ours with our new GPS systems, and then the regional systems by the Indians and the Japanese. And what you see in the center is basically it's a chart of what we might expect, how many satellites we might expect to see in the sky at any particular time. And you can see that over the Indian Ocean and Southern Asia and the Western Pacific, there is a dramatic concentration of these satellites, which will improve our ability to apply these systems to geohazards, resilience, and understanding mitigation. There are up to 35 satellites available at any particular time, and today GPS in this region we might expect 5 or 6. So let's look at some of the advantages here. On the right, on the left, you see positioning capability of GPS in the present day. And GPS really can provide, if it's sufficiently processed, accuracies on the order of 2 centimeters. But generally, in the vertical, it's about 4 centimeters. And as we add these systems together, whether it's GLONASS or COMPASS or etc., if we add these together, the accuracy is improved significantly. And the processing requirements are minimized because the errors tend to average out. And so given any place in the world today, we can pretty much provide a real-time navigation within a volume about the size of a Rubik's Cube. And if we're willing to wait a couple of 4 hours or so, we can produce navigation within the constraints of a sugar cube on the order of a centimeter or so. Some of these applications of GNSS early on, we began to look at orbiting GPS receivers in space. And in fact, the very first receivers were put on the NSF GPS MET mission. They were basically a JPL turbo rogue that was really flight tested, and those and the components hardened. And it was very successful. Okay, thanks. And it provided a good understanding of the refraction of the atmosphere as the rays between the fast orbit of the GPS receivers and the slower orbit of the GPS satellite, the transmitting satellite, the occultation would occur because that the transmitting satellite would disappear from sight, but the atmosphere would bend the signal around, and that bending was an indication of the temperature and pressure of the atmosphere. And the same thing can apply to the ionosphere. So GPS was very inexpensive to do, and yet in partnership with Taiwan, NSF, NOAA, and NASA worked to put up a constellation of 6 of these, and it cost us less than $100 million. And the ECMWF, the European Weather Forecasting Group, has rated the early cosmic mission as one of the 5 most important missions in the determination of atmospheric dynamics. And it's certainly in a cost class far different. Now we're looking at a cosmic tube. These initial cosmic satellites are fading away. And the new cosmic satellites will be able to look at all of the constellations. And here you see what the effect would be of the cosmic tube occultation density using simply GLONASS and GPS. In red, you can see what predated that capability, and still somewhat today occurs, the launching of radiosonde balloons. And certainly not as effective. And global synoptic views of the atmosphere is something that are becoming a daily reality. Let's go back to those GNSS sites. All of those sites actually provide us with a measurement capability of the environment on the Earth's surface. And this is something called GPS reflectometry. Basically, we're looking at the reflection or the interaction of waves reflected from the ground up to the GPS antenna, and that with respect to the signal directly from the satellite. Now, you might expect, if you know something about electromagnetics, that upon reflection, the GPS signal coming from the satellite is circularly polarized right hand, and that reflected from the ground should be left hand, and therefore there should be no interaction. Well, in reality, there is about 10 or 20% of a left-handed or right-handed circular polarized signal that remains, and that produces interference at the antenna, and so you find an oscillation or modulation of the received GPS signal, and its effect is on the signal-to-noise ratio. Analyzing that can give you, and knowing what the height of the antenna is and the position of the transmitting satellite, gives you an idea of the part of the ground that you're looking at and the intensity of the modulation. And from this, you can determine the height of the reflecting signal and something a bit more about its characteristics. This can be applied to soil moisture, can be applied to snow cover, it can be applied to vegetation, biomass, and it can be applied to sea level. Sea level is one example here. You can see the low tide situation in Alaska versus high tide, very high tides. And here you see a GPS tide meter, basically tide gauge. It's normally you find GPS position near the tide gauge to remove ground motion. Well, in this case, GPS can do both, and it doesn't require constant maintenance. This is a signal that compares the tide gauge signal in red to the observed SNR changes at the GPS receiver. And I think you'll agree that this is could be a very useful technique. It's still in the development stage, although a good deal of the receivers in the western U.S. are being used for these purposes. Now let's go to real-time GPS. Unfortunately, we aren't quite as successful in the application of real-time GPS. If we're going to address geohazards, we must receive these signals in real time to be effective. Unfortunately, there are political, commercial, and communications limitations that keep us from fully developing this capability. But I think in this case, perseverance is the byword here. We need to persevere. We also need a good example of where we can apply these capabilities. And on Boxing Day in 2004 at Phuket Island in Thailand, these folks were out wandering the beach because suddenly the water withdrew and exposed flopping fish and crustaceans. Very interesting. Until suddenly they looked up and saw this big white wave approaching. They should have had warning. The earthquake that caused this was a megathrust earthquake in western Sumatra, Banda Aceh. Those people, there were over 200,000 people lost in that region. They had no warning, absolutely no warning. In Thailand, they should have had an hour to understand that there was a tsunami approaching. But these folks had no warning. And if you look up in the upper right, you can see there have been many, many of these major tsunamis. Usually caused by, all of these are caused by megathrust earthquakes. And what we're trying to develop is a more effective and efficient warning system. These things don't occur every year, and so any system that we implement needs to be able to address and sustain itself through the long periods between tsunamis. We have, in order to understand the capabilities required, if we look at the time between basically the trench gap and the shore, we can understand how long it would take for a tsunami to approach land given proximal hypocenter. And in this case, it looks like it's on the order of 5 minutes or less is what we need. And Diego Melgar examined the entire ring of fire to understand the ranges that were necessary. But 5 minutes is what we need to do. We also understand about 7 years after the tsunami in Sumatra, there was a very significant tsunami in Japan, the Tohoku Tsunami. Now, it was understood from the Sumatran tsunami that the failure was largely because of an inability to measure the magnitude of the earthquake, the causative earthquake. And shortly thereafter, there were 3 publications. One was Jeff Blewett, who understood, and actually it wasn't Jeff Blewett, it was a whole assortment of his colleagues that published this, that tsunami could have been predicted within 15 minutes if if the GPS data in the vicinity, in the region, would have been analyzed in real time. We could have estimated the size of that, the magnitude of that earthquake. Then Tony Song recognized that simply the displacement that could be measured from in the region of the tsunami could have actually been used to model the tsunami. And then finally, a German researcher showed that we needed to be a bit more careful and to develop a distribution of GPS receivers throughout the Indo-Pacific region, but something on the order of 2 receivers every 100 kilometers or so, in order to fully understand the dynamics of that earthquake. So steps to tsunami warning would be developing a reliable and available real-time communications from the GNSS receivers at subduction zones. One of the important things here is their sustainability. These GPS receivers during the course of the day would do far more than simply look for major earthquake dislocations. They can serve society by increasing the local network accuracy. They compute the real-time displacement, detect events and compute displacements, basically, and estimate the earthquake source model, and then propagate that warning to agencies. So what we've been doing in the past few years, there are at least 3 approaches. Here is one of them to understanding how to estimate the earthquake displacement and develop tsunamis, and that's basically from static displacement of the land mass. And from that, you can create a centroid moment tensor. Similar to Japan, we have a number of real-time GPS receivers along the West Coast, largely supported by state and federal agencies, and some of these supported by NSF, some by the USGS and the various states in the region. And we've tried to link these under a READY program to develop an operational prototype tsunami warning network. And that's moving forward quite nicely. And NOAA is very much interested and involved in accessing these systems. So we're hopeful that we will be able to bridge the divide here between research and operations, one of a very difficult mission. Let's go back to Tohoku, and you can see this is basically the reaction of the ionosphere to that Tohoku earthquake and tsunami. And you can see these rings of emanating signals from the hypocenter. Those are gravity waves in the ionosphere. They're reacting to the acoustic coupling between modulation of the Earth's surface through the tsunami, initial uplift in tsunami, and the ionospheric waves. Hopefully this will. Now this is from using only GPS receivers. So I think there are something like 6 GPS receivers involved here. As we indicated earlier, as the GNSS receivers improve, there will be 6 times this number. So basically it's like going from a poor resolution television signal of a decade ago to high resolution images of the ionosphere. So this will be a very important tool for us as the GNSS signals develop The process basically is indicated on the left. This is a very old result from done, I think, in the early 70s that showed that surface waves on the Earth's surface could induce gravity waves in the ionosphere. The time for the propagation of those signals is about 6 minutes. And if we had an effective way of measuring the ionospheric undulations, then we could basically watch the approaching tsunami. Well, GPS provides that because it looks out over the horizon. And because dual frequency GPS can provide estimates of the total electron content, we can actually see these waves approaching. And basically the maximum effective range of this capability is about 1,000 miles from the actual receiver. So here you see what if we simply took the available IGS, International GNSS service receivers, we can see we pretty much cover the oceans. Now, with the addition of a few more buoys, etc., we could do far better. Now, we held a meeting in Sendai earlier in July, and at this meeting there was an announcement that JPL, through its GD GPS system, was going to implement a real-time capability using its distribution of some 100-odd real-time receivers globally. And the important item here, what you see is, it's a little complicated, but there are many receivers on Hawaii, and each one looks up into the atmosphere at a given GPS satellite. So the small offsets between these receivers, and they're necessarily small on Hawaii, produces, if you couple these together, it's like a scan of the ionosphere. And here you see correlations between waves. Now these waves are from a tsunami created by a major earthquake on Vancouver Island. And here you see these receivers. The individual dots that you see are the piercing points. Those are the points at which the rays from the GPS receivers to the GPS satellites penetrate the ionosphere. So they give you an accurate view of the dynamics of the ionosphere directly, which overlooks a portion of the ocean below. And I think you can see as this signal progresses the oscillation in the total electron content. But trust me, it's there. So this is a great advance because we now have a real-time capability to observe ocean deformation from GPS satellites, GPS receivers on the ground. So finally, how would we, where are we, what are the emerging opportunities, and what are the challenges? Well, the emerging opportunities are that geodesy continues to improve its accuracy. We will be achieving a 1 millimeter accuracy in our networks. We will be increasing the number of GNSS satellites by 3 to 6 times, depending on your location on the surface of the Earth, which will improve our resolution and our ability to identify events. We will be increasing the density of ground GNSS networks to also increase our resolution of events. And there is improving global broadband capability. For example, the Iridium constellation is being expanded, which will allow us basically global access to the real-time broadcasts of GPS receivers, and if we can afford to do it. So the challenges before us are political, institutional, and commercial constraints, which are concerned largely about national security, profits, and also the not invented here concept, because a lot of many operational agencies are committed to a particular technology. So we need to penetrate that. We need to cross from research to operations. A very difficult effort, which is posed to many others. We need coordination and cooperation amongst international and national agencies. We need to continue the densification of GNSS networks in underdeveloped countries. The UN is striving to achieve this through its UNGGIM program. And finally, we need better access to global broadband communications. So thank you. Many of these topics on tsunamis were addressed by a workshop held in Sendai, Japan in July. We are working on preparation of that report, and we hope to make it available in the very near future. Thank you very much.
As we grow old, we start going to the doctor. And the doctor would like to see your blood sugar, blood pressure, and all the lab results before he prescribes the medicine. Earth is becoming old, and we have to follow an integrated approach to study the land, ocean, atmosphere, ionosphere, which are associated with all kinds of natural hazards. And I'm very happy that John has given an overview and how the geodetic system has developed to monitor the land, ocean, atmosphere, ionosphere. Okay. So thank you, John. And we have reached time for a few questions. So if you want to ask any question, please come to the mic, okay? And John will be happy to answer. Okay. Can you identify yourself?
Sure, Molly Brown, University of Maryland. I'm interested in the parts of the world that are poorly represented, like the middle of Africa, right? Where there are no sensors, there's no cell phone towers, and there's precious few satellite resources. So although I know this is not your interest, can you say a few words about whether or not any of those 100 and some odd sensors are going to cover, like the Sudan, for example?
I agree with you. The central part of Africa is a very difficult region, not only because it lacks infrastructure, but because it lacks the capability to develop and retain experts in these capabilities. As soon as a person develops a certain expertise, he's quickly snatched up by the local mining agency or some technological company. So it's very difficult to find devoted scientists. The infrastructure, yes, it is problematic. And also, to some degree, the safety of these capabilities is problematic. In some places, such as Nigeria, where we've been developing NASA has been developing a ground station. We've been very concerned with developing capabilities in Africa, and we will continue. And I know that Gerald Bodden, who's here, has taken up that task as well. I know that UNAFCO is interested in developing these capabilities. Another region that is very much related to tsunamis, which needs further investment, is in the Southwest Pacific. Many of these small islands lack communications and lack the infrastructure. And what we've found is that there may be an opening here where natural hazards combines its requirements with those of the surveying and mining communities and fisheries. And if we can go as in a unified way to the local governments and also the international financing arms, that hopefully we can advance those capabilities.
Any other question? No question? Okay, Jim. The Gilbert Award, the lecture award, now we have converted into award, and you look for the nomination, and the next year the award will be given to you on Wednesday, okay, on the honors day. Okay, so it is our duty on behalf of the Natural Hazards Focus Group to give this medal. We come up to John LaBrecque, and it is written the AGU Natural Hazards Focus Group recognizes John LaBrecque, the 2017 Gilbert White Distinguished Lecture for original contribution to the basic knowledge of natural hazards or disaster risk. Okay, John. Not only this, we also have certificate given to John. Thank you very much.
Thank you.